All right, today we're going deep, literally, inside the skull. We're going to tackle a massive medical emergency, increased intracranial pressure. It's this bizarre situation where the very thing that's supposed to protect your brain ends up becoming its most dangerous prison.
I mean, think about it. Your skull. It's an incredible piece of engineering, right? It's a fortress made of bone, designed to keep your brain safe. But what happens when that very fortress becomes a cage? When the brain inside starts to swell and has literally nowhere to go? That's the crazy paradox we're diving into.
Okay, so let's start with the basics. The skull is basically a rigid box. After you're a kid, all those bony plates fuse together into one solid, unyielding container. And look, that's fantastic for, taking a hit, but it creates a massive problem when things go wrong inside, like say, your brain swells from an injury or a tumor starts to grow.
So what is intracranial pressure, or ICP, anyway? Well, just think of it as the pressure inside that closed-off box. It's generated by the three things that are crammed in there. You've got the brain tissue itself, all the blood that's flowing through it, and this stuff called cerebral spinal fluid, or CSF, which is kind of like a built-in shock absorber.
Okay, so how much pressure is too much? Well, in the medical world, they measure it in millimeters of mercury. And there's a really important number you need to remember: 20. Think of 20 as the safety ceiling. Anything below that, you're pretty much in the clear. But the moment you start creeping above 20, well, that's when all the alarms start blaring.
So you might be wondering, how does the body normally manage all this? It's such a delicate balance. Well, it all comes down to this really fundamental rule, a concept from both physics and biology called the Monro-Kellie doctrine. And I'm telling you, once you get this one idea, everything else we're going to talk about with ICP just clicks right into place.
So take a look here. Think of the inside of your skull as a small apartment with 3 roommates who can't be squished. The biggest roommate, by far, is the brain tissue. It takes up about 80% of the real estate. Then you've got the other 2, blood and that cerebral spinal fluid, the CSF, each taking up about 10%. These 3 are our key players, and they're in a very, very high-stakes game.
And here it is, the heart of the Monro-Kellie doctrine. Because that skull apartment can't get any bigger. If one of the roommates suddenly takes up more space, let's say the brain swells up after a hit, then one or both of the others has to shrink to make room. It is a zero-sum game, a really, really delicate balancing act.
But what happens when that balance fails? When there's no more room to give? Well, that's when the skull turns into something like a pressure cooker.
At first, the body is actually incredibly clever. It has these little tricks up its sleeve. It starts by pushing some of that watery CSF out of the head and down into the spinal canal. At the same time, it squeezes some of the venous blood out of the skull. It's basically buying itself time, and for a little while, this works beautifully. The pressure stays stable. But here's the problem. Those safety valves, they don't last forever. Eventually, you run out of CSF and blood that you can easily push out. And at that moment, the system loses all of its wiggle room, what doctors call compliance. And this is the truly terrifying part, because now even a tiny, tiny little increase in volume causes a massive, absolutely catastrophic spike in pressure.
So why? Why is that pressure spike so incredibly dangerous? Well, it all boils down to this absolutely critical concept: cerebral perfusion pressure, or CPP. The easiest way to think about CPP is as the force that's pushing blood into the brain. It's a constant tug of war. You've got your main arterial blood pressure, or MAP, pushing oxygenated blood in, and you've got the intracranial pressure, the ICP, pushing right back out. So you can see where this is going, right? As that ICP inside the skull skyrockets, it starts winning that tug of war. It literally starts to squeeze the arteries shut and choke off the blood supply. Your CPP just plummets. And when that happens, the brain tissue begins to starve for blood and oxygen. That condition is called cerebral ischemia, and that is what causes permanent, irreversible brain damage.
Okay, but a body in this much trouble doesn't usually go down without a fight. It starts sending out distress signals, basically sounding the alarm. So, what are these signals? What should we be looking for?
The early signs can be kind of tricky because they might seem like other things. We're talking about a headache that is just relentless, maybe sudden vomiting, and weirdly, it often happens without any nausea first. A person might get more and more confused or sleepy, their vision might get blurry, or they'll see double, and one of the key things a doctor will look for in the back of the eye is something called papilledema. That's when the optic nerve itself starts to swell from the pressure. Now, if those early warnings are missed, or things get worse really fast, the body sends out its last, most desperate, and frankly, most ominous alarm. It's a very specific, very strange pattern called Cushing's triad. It's three things happening all at once. The blood pressure goes through the roof, but the heart rate drops way, way down, and the person's breathing becomes completely chaotic and irregular.
And this triad, it's not random at all. It's actually the brainstem, the most primitive part of our brain, making a last-ditch effort to survive. It feels itself being starved of blood, so it literally screams at the rest of the body to jack up the blood pressure to force more blood into the head. But then, that super high blood pressure triggers another reflex throughout the body that slows the heart way down. It's like a physiological civil war, and it is a massive red flag that the brain is about to herniate.
So, the final, terrifying question. What happens if that final alarm is ignored? What happens when there's absolutely nowhere left for that pressure to go?
Brain herniation. It's the absolute worst-case scenario. The pressure inside gets so incredibly high that the soft brain tissue literally has no place left to go, except down. It gets forced and squeezed through the small opening at the base of the skull, and in the process, it crushes the brainstem, the very part of our brain that controls breathing, your heartbeat, your consciousness.
Okay, I know that sounds incredibly bleak, but this is where modern medicine steps in and fights back. And what's so cool is that every single thing doctors do is designed to do one thing: reverse that pressure crisis. And they do it by going right back to that Monro-Kellie doctrine and messing with one of those three components. So what are the first moves? Well, they're often surprisingly simple but really effective. Step one is always to make sure the patient is breathing well and getting plenty of oxygen. Then, there are two little positioning tricks. You lift the head of the bed up to about 30 degrees, and you make sure the neck is kept perfectly straight, not kinked to one side. So I do this. It's all about using gravity to help the blood drain out of the head more easily, which helps lower the pressure.
All right, after those first steps, doctors get more aggressive. They go on the offensive, directly targeting the stuff inside the skull. Remember that big 80% chunk, the brain tissue? Well, they can give powerful medicines, like mannitol, that literally pull water out of the brain cells to shrink it. And what about the CSF? For that, they can actually insert a tiny drain, called an EVD, right into the brain to physically drain that excess fluid out.
And then there's the last resort, the Hail Mary. When nothing else is working, there's a really dramatic procedure called a decompressive craniectomy. The logic is simple. If you can't shrink what's inside the box, you have to make the box bigger. Surgeons will literally remove a big piece of the skull bone, completely breaking that rigid box rule we started with. This opens the whole system up and finally gives that swelling brain room to expand without destroying itself.
So you see, we've come completely full circle. The skull is, without a doubt, our brain's best armor, its greatest protector. But as we've seen, managing increased intracranial pressure is this constant, desperate battle against those very walls. It shows us that the ultimate challenge for doctors isn't just about lowering a number. It's about figuring out how you save the brain from its own protector.